Okay, let's unpack this. When you think about welding, right, you probably imagine sparks, molten metal.
Yeah, the sort of dramatic stuff, the fire and noise.
Exactly. Maybe even the sheer force holding these huge structures together. But what if I told you one of the most critical steps for that strength happens, well, before the welding arc even ignites? We're taking a deep dive today into a hidden hero, you could say, of strong, durable structures, preheat in welding.
And it's fascinating, isn't it, how just, strategically applying heat before you even start welding can be the actual make or break factor for a joint's integrity.
Make or break, really?
Oh, absolutely.
Yeah.
So using your source material, that's ch23.pdf, we're going to uncover why this preheating is so vital, how it's applied, how it's controlled quite rigorously, actually, and why it's considered, well, just essential in metal fabrication.
So for someone hearing this maybe for the first time, the obvious question jumps out, right? Why would you heat something up just to heat it up again with the weld?
Yeah, that's the logical question.
What exactly is preheat? How does it fit in?
Okay, perfect place to start. So at its core, preheat is applying heat to the workpiece right in the weld zone immediately before you do any welding.
Immediately before.
Immediately before. And that includes even just tack welding. Your source mentions common ways are like a gas torch or an induction system, but there are others too. Definitely not just a casual warm-up. It's a very deliberate engineered step.
Right. And what's the main problem it's trying to solve? I guess it's not just about making the metal softer, easier to weld.
That's a really good point. I mean, it does help with weldability overall, but the main reason we use preheat, especially in welding steels, is to assist in removing hydrogen from the weld.
Hydrogen?
Yeah, hydrogen.
Oh.
Think of it like this invisible enemy lurking in there. If you don't manage it, it can lead to, well, catastrophic cracking later on.
Hydrogen in the weld. Wow, okay, that sounds like a really serious unseen threat. How does preheating actually help with that specifically? And are there other benefits too?
Oh, it's a huge threat. And preheat gives you several crucial advantages to stop those defects and make sure the weld is strong long term. Firstly, it slows down the cooling rate.
Okay.
Both of the weld itself and also the area right next to it, what we call the heat effective zone, or HAZ. That's the base metal that didn't melt, but its structure got changed by the heat.
Right, the HAC.
So this slower cooling significantly reduces the risk of hard, brittle microstructures forming in that zone.
Ah, okay. So it's like letting something cool down gently instead of like shocking it with cold so it doesn't become fragile.
That's a great analogy, exactly. And this gentle, slower cooling rate gives any absorbed hydrogen more time, more opportunity to diffuse out, to escape the weld metal before it gets trapped as it cools.
I see.
And that process dramatically reduces the potential for cracking specifically, a type often called cold cracking or hydrogen-induced cracking.
Okay, so slower cooling equals less brittleness, indeed less hydrogen cracking. Makes sense.
Precisely. Plus, another benefit. Preheat also effectively removes moisture from the weld preparation area.
Gets rid of water beforehand.
Yeah, and moisture is a big source of hydrogen in the first place, so drying it out is a huge plus. And beyond that, preheat actually improves the overall fusion characteristics when you're welding, and it helps ensure more uniform expansion and contraction.
Uniform expansion, meaning less stress.
You got it. That uniformity lowers the internal stresses that can build up between the weld metal and the parent material. It just makes for a much more robust, less stressed joint overall.
That's really quite something. It's so clear it's not just about, melting metal together. It's about controlling these invisible microscopic processes that genuinely dictate if a weld's going to hold strong or fail down the line. It's like engineering integrity from the inside out.
It absolutely is.
Yeah.
And to get that precise control, welding standards are, well, they're meticulous about defining different temperature stages. Your source clearly lays them out.
Okay.
So first, you've got the preheat temperature. This is the temperature of the workpiece in that weld zone immediately before any welding operation. Like I said, even tack welding.
Got it. The starting point.
Right. And it's usually expressed as a minimum temperature you have to hit. Sometimes it might be a range, but usually a minimum.
Okay, so that's the baseline before you start. What about once the welding is actually going, especially if it takes multiple passes?
Good question. That's where the interpass temperature comes in. This is the temperature during the welding process, specifically between passes if you're doing a multi-run weld.
Between the layers, kind of.
Exactly. Between the layers or runs. And it also applies to the adjacent base metal right before you lay down the next run. Now, this one is normally expressed as a maximum temperature.
A maximum. So you don't want it getting too hot between passes.
Precisely. But critically, It also should never drop below that minimum preheat temperature you started with. So it's a window you need to stay within.
Okay, temperature window. And what if something interrupts the welding? Shift change, equipment problem, maybe just a break. Does that mess everything up?
It could, which is exactly why there's a third critical temperature defined. The preheat maintenance temperature? Maintenance temperature, okay.
This is the minimum temperature in that weld zone that must be maintained if welding gets interrupted for any reason. And crucially, the source emphasizes it should be monitored the whole time during that interruption.
So you have to keep it warm even when you're not welding.
You have to keep it above that minimum maintenance level, yeah. It really is, like you said earlier, a carefully orchestrated dance of heating and timing, not just a vague, keep it warm idea.
Definitely sounds like a highly precise operation.
Yeah.
So how do they actually apply this heat in the real world? I mean, I picture a big torch, but what other methods get used?
Yeah, the big torch is common. That's flame-applied preheat, using torches or burners, usually with oxygen and a fuel gas like acetylene or maybe propane or methane. That's very common.
Right.
But we also see things like resistive heating elements, basically like big electric blanket elements.
Okay.
Or high-frequency induction heating, which uses magnetic fields to generate heat inside the metal itself through molecular agitation.
Oh, interesting. Like an induction cooktop, but for steel? Sort of, yeah, same principle. And for really big components, or when you need super uniform heating, they might even use large gas or electric ovens to heat the entire section before welding.
Wow, okay.
And there's also that distinction between just heating locally, right around the weld, which uses less energy, but might cause some uneven stress, versus global heating the whole part, which takes more energy but gives you that really uniform expansion and contraction we talked about.
Okay, lots of methods. So once the heat's applied, whichever way they do it, how do you actually know you've hit those very specific temperatures you mentioned? Where do you measure and when, especially if you've got a thick chunk of steel?
Yeah, that's where the rigor really comes in. The measurement has to be taken immediately before the welding arc passes over that spot.
Yeah, before the arc.
Immediately before. And where you measure depends a lot on how thick the workpiece is. The source gives specific rules. For thinner stuff, say up to 50 millimeters thick, you measure within a certain distance of the weld, typically 4 times the thickness, up to a max of 50 millimeters away, and usually on the same side the welder's working on.
Right.
But for thicker sections, over 50 millimeters, you measure a bit further out, minimum 75 millimeters away. And importantly, wherever practical, the source says you should try to measure on the face opposite to the one being heated.
Opposite. Why is that?
To make sure the heat has soaked all the way through the thickness, not just heated the surface where the torch was.
Ensures a deep, even heat.
Exactly. And that ties into another key point. You need to allow time for the temperature to equalize. A common rule of thumb mentioned is about 2 minutes for every 25 millimeters of thickness.
2 minutes per inch, basically.
Roughly, yeah. You need that time for the heat to distribute evenly through the metal. If you measure too soon, especially with flame heating, you might just be reading the surface temperature, which could be much higher than the core temperature. That gives you a misleading, potentially unsafe reading.
That makes total sense. Thicker metal needs more time, measure further out, maybe even on the backside, to get the real internal temperature. So what tools do welders and inspectors actually use for these measurements? And how reliable are they?
Good question. The source outlines a few common methods, each with its pros and cons. You've got things like temperature-sensitive materials, often called temperature crayons, or sticks, like Tempilstica or thermochrome.
Oh, crayons.
Yeah, basically. They're cheap, super easy to use. You mark the metal, and the mark melts or changes appearance when it hits a specific temperature. But, and this is crucial, they don't measure the actual temperature. They just tell you if you've reached a certain preset temperature. It's more like a go-no-go gauge for that one specific temp.
Okay, so useful, but limited. What gives you an actual number?
Right. For an actual reading, you've got contact thermometers. These often use things like bimetallic strips or thermistors. They do give you an accurate real-time temperature reading.
That sounds better.
It is, but they usually need regular calibration to stay accurate. And they're often limited to sort of moderate temperatures. The source mentions up to about 350 degrees C.
Okay, so good for many preheat ranges, but maybe not everything. What else?
Well, for wider temperature ranges, and especially if you need continuous monitoring, thermocouples are very common. They work based on thermoelectric potential differences between dissimilar metals.
Right, thermocouples. I've heard of those.
Yeah, they're accurate. They give you the actual temperature. They can cover a really wide range, and you can hook them up for continuous recording. They do need calibration too, of course.
Okay. Any other options, maybe for really high temps or tricky spots?
Yeah, for very high temperatures, or if you need to measure from a distance, you might see optical or electrical devices. Things like infrared pyrometers or optical pyrometers.
Like the temperature guns?
Exactly like that principle. They measure the radiant energy coming off the hot surface. They're great for non-contact measurements, but they tend to be much more complex, definitely more expensive, and usually reserved for measuring pretty high temperatures, maybe less common for standard preheat ranges, but definitely used.
Okay, quite a range of tools for the job.
Okay.
Now, this level of detail about preheat, the specific temps, the measurement rules, it's fascinating, but why does all this meticulous control matter so much beyond just, doing it right? What are the real-world consequences if someone cuts corners, maybe skips a preheat they thought was minor?
It matters, well, immensely. Because these temperatures, the preheat, the interpass temps, they aren't just suggestions pulled out of thin air. They're specifically calculated using established methods found in major industry standards.
Like codes and specifications?
Exactly. Your source mentions examples like BSEN 1011-2 from the British standards or AWSD 1.1 from the American Welding Society. These standards tell you how to figure out the required temperatures based on the materials, the thickness, the welding process, and so on. Then those calculated temperatures get validated. They get tested and proven during the formal qualification of the welding procedure.
Ah, the WPS, the welding procedure specification.
Precisely. And here's the really critical part. According to major qualification standards like DSEN, ISO 15614, or ASME Section 9, both the preheat temperature and the interpass temperature are classified as essential variables.
Essential variables. Okay, that sounds pretty important. What does that mean in practice? What's the impact if someone just decides to, say, preheat a bit less or let the interpass temp drift too high?
It's more than just important. It means you've basically invalidated the qualified procedure, the proven recipe for that weld. Any change outside the qualified range for an essential variable, like preheat or interpass temperature, requires a completely new procedure qualification test.
Wow, a whole new test.
Yep.
Just for changing the preheat slightly.
If it goes outside the permitted range, yes. It's not a suggestion. It's often a contractual and regulatory requirement. It ensures the safety, the quality, the fundamental integrity of that weld.
Right.
And by extension, the whole structure it's part of. You can't just wing it.
So the inspector plays a key role here then?
Absolutely critical. The welding inspector constantly refers back to that approved WPS for all the requirements, including preheat and interpass. And if there's any doubt or ambiguity, they consult with senior inspectors or engineers. There's no room for guesswork when it comes to essential variables.
So yeah, it's crystal clear now. Preheat isn't just some simple warm-up routine. It's this calculated, incredibly precise, and utterly critical step that's controlling microscopic changes deep inside the metal. It's preventing brittleness, stopping those hydrogen cracks, and ultimately ensuring the strength and really the longevity of the weld.
And if you zoom out, look at the bigger picture. That level of detail, the control required just for preheating, it really underscores the sophisticated science and engineering that goes into what might seem like basic industrial processes, doesn't it?
It really does.
It's a powerful reminder, I think, that building robust things isn't just about the parts you can see. It's about the invisible integrity that's carefully engineered into every single connection, every joint.
So the next time you see a welded structure, could be a bridge, a building, maybe even just a piece of machinery, take a second to consider that unseen heat, those carefully watched temperatures, and the hidden science, the microscopic battle, that's making sure it all holds together safely. Makes you wonder, what other simple processes out there are hiding that kind of fascinating complexity?
Good question to ponder.
Thank you for joining us for this deep dive. We really hope you're leaving maybe a little more informed and definitely a lot more curious.